In addition to having your sort of typical Bronsted acids where there's very clearly an acidic proton, there's another class of acids called anhydrous oxides. And this is sort of, you can think about these as Bronsted acids that have their water molecule or more than one water molecules removed in some cases away from them. But when you dissolve them in water, they will produce hydronium. Okay, or equivalent way of thinking about it is that they will react with hydroxide. Either way, they're acidic if they do this. Okay, they're acidic oxides. So CO2 is an example of an acidic oxide, and it's an anhydrous oxide that happens to be acidic. Okay, why is that? Well, you can think of CO2 as the anhydrous form of carbonic acid. Okay, because you just remove water from carbonic acid and get CO2. Carbonic acid, of course, can react with water to generate a hydronium ion. So if you bubble CO2 into water, you will be increasing its acidity, decreasing its pH. Seltzer water is always going to have a lower pH than the corresponding pure water. Okay. And so that is an acidic oxide. Basic oxides, it's the opposite. They're anhydrous oxides that when you dissolve them in water, they produce OH minus, they produce hydroxide, or equivalently, they react with an acid, right? Hydronium. So barium oxide is sort of a classic example. You throw some barium oxide in water, and you're going to get barium ions and hydroxide being formed. And then there's amphoteric oxides. These can act as bases or acids when dissolved in water. And usually this is going to depend upon what pH you're at. Okay, so maybe if you're at a certain pH, it'll act as a base, like if you're in, okay, or if you're in another pH, it'll act as an acid, same compound. So gallium oxide is an example of an amphoteric oxide. It can react with an acid, okay? So this would be acting as a base because it's reacting with hydronium, okay, to make this gallium hexaqua complex. Or if you're under basic conditions, right, it can react with base to give you this other species, okay, where you have hydroxide coordinated, and this would gallium here would be acting as an acid, right, because it's reacting with OH minus. So under acidic conditions where you have a lot of hydronium around, it's going to react in one way. Under basic conditions where you have a lot of hydroxide around, and amphoteric acid is going to act another way. It's going to act as an acid. Metal oxides tend to be much more basic than non-metal oxides. And why would this be? And so the reasoning here is that it has to do with covalent versus ionic bonds, right? And so for non-metals like look at CO2, right? You can think about this. Non-metals we know like to form covalent bonds, right? So you can think about carbonic acid as being CO2 covalently bonded to water. And so if it's covalently bonded, that's going to give you one mode of reactivity. But if you think about barium hydroxide, and you think about it as being barium's a metal, so much more likely to form ionic complexes, it's going to much more likely form a barium ion, okay? Whereas an acidic oxide, you're thinking about this as a covalent compound. That covalent compound can then go on to give off the proton, acidic, okay? But here, the reactivity is very different. It's just forming an ion right away. It's like the barium wants to be a metal ion, and so it forms a ion right away. And in order to do that, it's giving off a hydroxide, so it makes a base. And so that's why metal oxides are more basic than non-metal oxides, okay? It's because of their ionic nature. All right, so based on that, you can come up with, well, trends in periodicity of oxide, anhydrous oxide acidity. And so oxides on the left of the periodic table are going to be strongly basic, okay, because that's where your metals are. And on the right, you're going to be strongly acidic. And so And in between, you're going to be somewhere in between, right? So you can see in the middle, you have some amphoteric. Okay, this is not showing the transition metals. We'll talk about that on the next slide. But on the very left, these are strong bases. Lithium hydroxide lithium oxide makes lithium hydroxide in solution. Okay. Um, when you get to the right side of the periodic table, like this would be what dichloro heptoxide. Okay, not a very common chemical that people deal with because it's really highly explosive. You're going to deal with a hydrated form of that, which is perchloric acid, very strong acid. Okay, but in the middle, you're going to have the amphoteric things. All right, so we can understand that trend. It's interesting with the amphotericism. Here is looking at the first row transition metal and anhydrous oxides. And if you look, you have the same general trend we talked about. As you go from left to right, you're going to get increasingly acidic. But the other thing that you notice here is oxidation state. Okay, and so let's just look at manganese to start out here. Manganese is more acidic when it's had a higher oxidation state. Okay, so like Mn2O. Anyway, manganese in its Mn2O7. There we go. Mn2O7. That's manganese in its +7 oxidation state. That's going to be very, very acidic when it dissolves in water. It's going to make permanganate acid, which is actually highly explosive as well. Okay, and why would higher oxidation states be more acidic than, let's say, just plain old manganese 2 oxide, MnO, which is basic. Okay, and in between you can see MnO2 is actually amphoteric. You can go both acid or base depending on the pH. Well, why would that be? It has to do with how much does this proton want to leave? Okay, so if you have a very high charge density on your central atom, that proton is going to want to leave very, very readily, right? So because you have a high positive charge formally on manganese here being +7, so it's going to want to leave. So I mentioned left to right on the periodic table, and on the transition metals, you get this getting more acidic. And if you just look at oxidation state 2, I mean, they're all basic. Zinc oxide, we would predict, would be more acidic than TiO, but you can't really see a trend here just looking at it in this coarse-grained way. But what you can see is that there is a shift in the onset, okay, of where amphoterism starts. So, from titanium to manganese, at oxidation state 4, you're amphoteric, which is halfway between acidic and basic, right? But you only have to go to oxidation state 3 when you're iron, cobalt, or nickel to already have some acidic character in there. So, there still is this left to right trend of becoming more acidic when you look at this a little bit more carefully. So amphoterism shifts to lower oxidation states in late transition metals. That is another way of saying that.